Imagine looking at a map of the universe and realizing that galaxies are not scattered randomly through space. They are not floating alone like tiny islands in an empty ocean. They are connected. They gather into clusters. Clusters gather into superclusters. And those superclusters stretch across space like giant threads of matter. The universe, when seen on its largest scales, begins to look less like empty darkness and more like a glowing web. Now imagine that in this web, astronomers found a structure so large that light itself would need more than 1 billion years to cross it. Not a galaxy, not a black hole, not a planet. A structure made from galaxy clusters, hot gas, dark matter, and gravity, stretched across a distance so massive that normal comparisons almost stop working. This structure is called Kipu, and right now it is one of the strongest candidates for the biggest structure ever found in space. Kipu was reported in 2025 by a team led by Hans Boehringer. The discovery came from a study of the nearby universe, not the edge of the observable universe. That is what makes it even more interesting. This giant was not hiding at the farthest possible distance, where everything is ancient and faint. It was found in the relatively nearby cosmic universe, between about 130 and 250 megaparsecs away. In light years, that means hundreds of millions of light years from Earth. In human terms, that is still unimaginably far. But in cosmic mapping, this is close enough that its gravity and structure may affect how we measure the universe around us. Kipu is longer than 400 megaparsecs. That is more than 1.3 billion light years. To understand the scale, start with Earth. Light can travel around Earth more than 7 times in 1 second. Light from the moon reaches us in about 1.3 seconds. Light from the sun takes about 8 minutes. Light across the Milky Way takes roughly 100,000 years. But light crossing Kipu would need more than 1 billion years. During that time, entire planets could change, species could rise and disappear, and civilizations could be born and vanish, while the light still had not crossed from one end of the structure to the other. The Milky Way itself is already enormous. It contains hundreds of billions of stars, and our solar system is just one tiny piece inside it. But compared with Kipu, the Milky Way becomes almost nothing. Kipu is not 2 or 3 times wider than our galaxy. It is thousands of times larger. If the Milky Way were a small coin, Kipu would not be a bigger coin. It would be a continent-size pattern drawn across the map. But size is only one part of the story. Kipu is also unbelievably massive. Its estimated mass is around 200 quadrillion times the mass of the Sun. One solar mass already represents almost all the matter in our solar system, because the Sun contains more than 99% of it. Now multiply that by 200 quadrillion. That is the kind of number astronomy forces us to face. It is not just big. It is violently beyond normal imagination. Still, Kipu is not a solid object. This is important. It is not a giant wall you could fly into like a surface. It is not a cosmic building or a single body. It is a superstructure, a huge arrangement of matter spread across space. It is made from galaxy clusters and connected filaments, with matter gathered into knots along a massive cosmic chain. The team named it Kipu because its shape reminded them of an ancient Andean recording system made from chords and knots. That name fits almost perfectly, because Kipu looks like the universe tied information into space using galaxies as knots. The way astronomers found it also matters. They did not just look at a beautiful telescope image and draw a shape around bright spots. They used galaxy clusters detected through X-ray observations. Galaxy clusters are among the largest gravitationally bound systems in the universe. They can contain hundreds or even thousands of galaxies, along with extremely hot gas and huge amounts of dark matter. The hot gas shines in X-rays, which makes galaxy clusters useful markers for tracing where the densest matter lies. The survey used for this work is called CLASSICS, which stand for Cosmic Large-Scale Structure in X-rays. By using X-ray galaxy clusters, researchers could map the matter distribution in a large part of the sky. That is how the structure appeared, not as one shining object, but as a pattern in the distribution of massive clusters. The dots connected, and a cosmic chord emerged. Kipu was not alone. The same study identified 5 major superstructures in the nearby universe. Kipu was the largest, but the others included famous names such as Shapley, Hercules, Serpens Corona Borealis, and Sculptor Pegasus. Together, these superstructures contain a major share of the galaxy clusters, galaxies, and matter inside the study volume. That means they are not small accidents in the data. They are major pieces of the local cosmic architecture. This is where the discovery becomes more than a record. A structure like Kipu can affect how we measure the universe. Cosmology depends on precision. Scientists measure the cosmic microwave background, the expansion of space, the motion of galaxies, and the way light is distorted by gravity. But if a giant nearby superstructure is sitting in the map, its gravity can create small but important effects. It can influence the motion of galaxies. It can distort background images through gravitational lensing. It can affect how radiation from the early universe appears to us. It can even complicate measurements of the Hubble constant, which describes how fast the universe is expanding. That does not mean Kipu breaks cosmology. That would be a cheap exaggeration. The standard model of cosmology, called lambda-CDM, already allows large structures to form. The research team compared these superstructures with simulations and found similar structures can appear in that model. So Kipu is not proof that everything scientists know is wrong, but it is a serious reminder that the nearby universe is not smooth and simple. It has giant lumps, huge flows, and massive structures that must be accounted for if we want precise answers. This connects to one of the deepest ideas in cosmology, the cosmological principle. On the largest scales, the universe is expected to look roughly the same everywhere and in every direction. Not exactly the same, but statistically smooth. This idea is one of the foundations of modern cosmology. But when astronomers find structures like Kipu, the question becomes sharper. How large can a structure become before it challenges that smoothness? How far must we zoom out before the universe stops looking like a web and starts looking evenly distributed? The answer is still being tested. Kipu does not automatically destroy the cosmological principle, but it pushes scientists to measure the boundary more carefully. It shows that even in the nearby universe, matter can be arranged into enormous patterns. These patterns are not just decorations. They influence galaxies, radiation, and measurements. One of the most interesting effects is connected to the cosmic microwave background. The cosmic microwave background is ancient light, left over from the early universe. It is one of the most important pieces of evidence for the Big Bang. Scientists study tiny temperature differences in this radiation to understand the universe's early conditions and evolution. But when this ancient light travels through huge, evolving gravitational fields, its energy can shift slightly. This is called the integrated Sachs-Wolf effect. Superstructures like Kipu may leave a faint imprint on that background radiation. The team looked for this kind of signal in Planck data. They found a signal with the expected strength, but with low significance. That means it is interesting, but not strong enough to treat as a final confirmed measurement. This is how real science works. It does not scream certainty when the evidence is still developing. It marks the signal, tests it, and waits for better data. Kipu also matters for galaxy evolution. Galaxies do not grow in isolation. Their environment changes them. A galaxy inside a crowded cluster lives a very different life from a galaxy drifting in a quiet region of space. In dense environments, galaxies can lose gas, collide, merge, slow down star formation, or be transformed by gravitational interactions. A superstructure like Kipu is not just a huge map feature. It is a cosmic environment where galaxy evolution happens under extreme conditions. This is one reason the discovery is powerful for storytelling. Kipu is not only the biggest structure, it is also a natural laboratory. It lets scientists study how matter gathers, how dark matter shapes visible structure, how galaxy clusters connect, and how the universe's expansion competes with gravity. Every part of it is a clue about how the universe built itself after the Big Bang. But there's a strange twist. Kipu may not last forever. These superstructures are not necessarily permanently bound as one object. The universe is expanding, and on scales as large, gravity does not always win everywhere. Some parts may collapse into smaller units, while other parts drift apart over cosmic time. That means Kipu may be a temporary configuration, a giant pattern that exists now, in this era of the universe, but will eventually break into smaller structures. That makes it even more dramatic. We are not looking at a permanent monument. We are looking at a phase in cosmic evolution, a structure billions of years in the making, visible to us now, but not frozen forever. The universe built it, and the universe may one day tear it apart. There is also a hidden part of the story. Some regions of the sky are difficult to study because our own Milky Way blocks the view. Dust, stars, and gas in our galaxy create what astronomers call the zone of avoidance. It is not a wall in space. It is a blocked viewing region from our perspective. Some parts of Kipu appear close to this hidden zone, which means future observations could reveal more detail. It is possible that better surveys may refine its shape or reveal connections that are not visible yet. This is why discoveries like Kipu are never truly finished. Astronomy is not just about seeing farther. It is about mapping better. Sometimes the universe hides things not because they are too distant, but because we have not yet connected the data correctly. A galaxy cluster here, another cluster there, a filament between them, a hidden region blocked by the Milky Way. And suddenly the map changes. What looked like separate points becomes a structure. What looked like empty space becomes part of a web. Kipu also forces us to be careful with viral space claims. You may have heard of other massive structures, like the Hercules Corona Borealis Great Wall, sometimes described as 10 billion light-years across. That sounds bigger than Kipu. But the problem is confirmation. Some claimed structures are based on patterns that may not represent a single connected concentration of matter. In science, the biggest number does not always win. The strongest evidence wins. Right now, Kipu has one of the strongest current claims because it is traced through galaxy clusters and published as a mapped superstructure in the nearby universe. That difference matters for a serious space channel. A weak claim can make a video feel big for 1 minute. But a strong claim makes the story last. Kipu does not need exaggeration. The real numbers are already insane. More than 1.3 billion light-years long. Around 200 quadrillion solar masses. Dozens of galaxy clusters. A structure large enough to matter for cosmological measurements. That is already bigger than most science fiction. The discovery also reveals something about humanity's position in the universe. We often talk as if Earth is standing outside the cosmos, looking in, but we're inside the map. Our galaxy is inside a local group. That local group is part of larger flows and structures. Those structures sit inside the cosmic web. We are not observers holding the universe in our hands. We are tiny points inside a structure so large that even our best maps are still incomplete. And maybe that is the real power of Kipu. It is not just that astronomers found something enormous. It is that the discovery shows how much of the universe is organized at scales far beyond human instinct. Space is not just empty distance between stars. It has architecture. It has filaments. It has walls, knots, bridges, voids, and flows. Gravity has been writing patterns into the universe for billions of years, and only now are we learning how to read them. The biggest structure ever found in space is not a giant object glowing in one telescope image. It is a cosmic pattern stretched across a billion light-years. It is a chain of galaxy clusters bound by gravity.